So one of the main advantages of using bottlenecks is reducing the number of parameters. And this is achieved by using smaller filters within the bottleneck layers. And this reduces the computational cost and makes the model more efficient. Another reason is a more efficient feature extraction. By reducing the dimensionality of the feature maps, bottleneck layers can condense the information and focus on the most important features. Because we're using less parameters, we improve generalization and prevent overfitting. Bottlenecks also enable deeper networks by mitigating the vanishing gradient problem, and they do that by reducing the number of parameters. And last but certainly not least is the use of bottlenecks in conjunction with residual connections, also called skip connections. This allows the network to learn identity mappings more effectively, which again helps with the vanishing gradient problem and allows for deeper networks. So this bottleneck idea came from this paper. The bottleneck residual block is a variant of the residual block. So you have this direct path to learn the identity mapping, but you also have this residual path with these one-by-one convolutions, therefore creating this bottleneck, and hence the name. Now, if we click here and go to bottleneck, this is the bottleneck of the ResNet architecture implemented in PyTorch, where you can see the conf 1x1, 3x3, and another 1x1, as you can see here. However, YOLOv5 uses a variant of this bottleneck where we're not using the last 1x1 convolution. We're doing a 1x1 and a 3x3. As you can see here, where we're performing 1x1 convolution right here and a 3x3 convolution. So we don't have that additional 1x1. And of course, we do have the identity mapping as well. Now here at the bottom, we're going to do what we did here, basically running the output of stage 1 through this C3 module and then getting the output of that module. But we're going to do it one step at a time. So let's go here. So we have a total of 13 tensor operations from the output of stage 1 to the output of stage 2. The name here is different so that we can then compare with the direct method that we obtain above and confirm that we get the same results. So the first thing that we're going to do is call that CV1, which is this convolution right here. And we're going to input the output from stage 1, and we're going to store it in this variable. And then this output will be the input to the bottleneck. So this output will be the input to the convolution CV1 for bottleneck 0. So remember, we have bottleneck 0, 1, and 2. This is not to be confused with this one right here. This is the type of the bottleneck. Basically, this is a bottleneck with residual connection. That's all this means. But we're going to have bottleneck 0, 1, and 2. So we'll feed this output to this convolution, and then we'll obtain this output, and then we'll feed that one to CV2 of bottleneck 0, and we'll obtain this output. And then here we're going to add the input to this bottleneck, which is this one right here. As you can see, the input to that same convolution and the output of the previous layer. We're going to add that to the output of this convolution. And this is not concatenation or anything like that. This is literally element-wise addition. We are literally adding the values from this tensor to the values of this tensor. They both have the same dimensions, so we can do that with no problem. And the result would be this output right here. So the result from this bottleneck 0. Now, given that we have 3 of them, this output will be the input to bottleneck 1. And we'll repeat that same operations that we did for bottleneck 1. So this input will become this output, which will be the input to the second convolution of bottleneck 1. And then we'll add those, the output from the previous convolution, as well as the output from convolution 2, bottleneck 1. We'll do the same one for bottleneck 2. So remember, bottleneck 0, 1, and 2. And the result of all of that, all of those bottlenecks, will go into a concatenate function. And the concatenate function takes the output from the last bottleneck, as you can see here, the output of bottleneck 2, but also the output from CV2. So this convolution gets concatenated with the output from the bottlenecks. And in this case, it's not addition, but actually concatenation, where we're adding, in this case, for dimension 1. So we started with 160 by 160 by 128. this became a 160 by 160 by 64. And once we perform this convolution, this also became 160 by 160 by 64. When we concatenate those, the result is a 160 by 160 by 128 again. So that's what the concatenation did. And then we convolve that one more time with CV3 to obtain the final output. Now, before we compare the result with the step-by-step method versus the direct method, the reason why we have multiple bottlenecks, in this case 3, is that by stacking multiple bottlenecks together, the network can learn more nuanced features from the input data, which is crucial for the accurate detection of objects in various sizes and shapes, according to Glenn Jacker, lead developer of YOLOv5. So let's run this. And again, you can see that the shape gets splitted between this one and this one, but then within the bottlenecks, we maintain the shapes. And this is possible because we're performing 1-by-1 convolution without any padding. And then here we're performing 3-by-3 convolution, but we're adding padding of 1 so that the input and the output shape remains the same. And you can see that, again, the number of channels gets split between part 2, meaning the convolution and the bottlenecks, and part 1. So you can see this 64 is the one that is fed here. And then we have through the other path 64. Those get concatenated right here. And we're using dimension 1. So dimension 0 and dimension 1. So we're adding dimension 1 to get 128 right here, just by inputting the dimension that we want to concatenate. So if we compare both results, we obtain true from torch.allClose, which returns true if the tensors are the same, meaning that they satisfy this condition right here, which states that at both this absolute and relative tolerance, they're the same. Now here above, we printed the shapes of the input and output tensors through this C3 module, but we can also print the shapes of the weights for these different convolutions. So let's do that here, which shows us that we have these 1-by-1 kernels for conv1, 2, and 3. Now we also see that the bottlenecks have these 1-by-1 and 3-by-3 for each of the bottlenecks, which prompts the questions of what are exactly 1-by-1 convolutions and why do we actually need them?